Okay, so welcome to lecture 2 of Introduction to Quantum Computation. Okay, this is the summer 2020 master's course at the University of Paderborn. So last week we talked mainly about math, right? We talked about linear algebra, and the claim was that this is the language we're going to use to talk about quantum computation. And so this week we'll finally start actually talking about quantum things. I'll start using the word quantum, okay? Some quick logistics before we begin. So last week I did release A1, right? That's due this Friday, May the 1st. Please do hand that in through Panda. There is a LaTeX source file available for it. I strongly recommend you write your solutions up in LaTeX. If you do any research in theoretical computer science, odds are you're going to be writing your papers in LaTeX anyway, so this is a perfect chance for you to get used to writing things up in LaTeX. Assignment 2 is released. It is due not this Friday, but the Friday afterwards. Okay, and all the assignments are available both online on the course website and also on Panda. Okay, so that's all the logistics I have for you guys this week. Let's begin with the lecture. Okay, so like I said, this week we're going to be talking about Introduction to Quantum Mechanics. The quote to open the lecture is the following. It's by Richard Feynman, a very famous physicist. It says, "The paradox, in quotes, is only a conflict between reality and your feeling of what reality ought to be." Okay, and so what this is referring to is that, as we'll start to see today, quantum mechanics, although it is a highly successful theory, it is notoriously counterintuitive, right? We still don't understand the mathematical laws. Okay, it's a set of laws basically that were developed in the early 20th century by many famous physicists, Max Planck, Albert Einstein, Erwin Schrödinger, and so forth. Okay, but even though the mathematical rules, these rules, what they do is they describe the world of tiny subatomic particles like electrons, photons, atoms. Even though the rules seem to work very well as far as experiments hold up, we don't know how to interpret them. What are these rules supposed to actually mean? Okay, and we'll see what that means in a second. Okay, and that's also what the quote is trying to get at, right? So you kind of have to let go of what your feeling of what reality ought to be to really kind of understand quantum mechanics. One of the most natural ways of thinking about quantum mechanics is the so-called Copenhagen Interpretation, which just basically says, shut up and calculate, right? I mean, forget about what the rules are supposed to mean. Just use the math works, and move forward, right? Okay, so for today's lecture, quantum mechanics basically can be modeled using 4 kind of postulates or main rules. And once you have those rules in place, you can kind of live in this magic sandbox and just work with those rules. Okay, you can think mathematically, you can forget about the physics behind it. And again, we're computer scientists, so that's precisely the view we're going to take. So the 4 postulates are going to be, how to describe individual quantum systems, how to describe quantum operations, how to describe composite or multiple quantum systems together, and finally, how to describe measurements. And in this lecture today, we're going to do the first 3 postulates. The 4th postulate deserves a discussion on its own, and we're going to leave that to next week. Okay, so let's begin with postulate 1, individual quantum systems. Okay, so 1.1 in the notes, postulate 1. Individual quantum systems. Okay, so the very basic starting point for this is going to be that, in a classical world, if I have a single bit, as you're well aware as computer scientists, right, classically, a bit takes on one of 2 values, right? It's either 0, and I'm going to write in red, or 1. Okay, so if I have a single bit, it's going to take on one of these 2 values, and if I want, I could flip a coin and say with probably 50% it's 0, with probably 50% it's 1. That's fine, that's fair game too. But that's basically the extent of what you're allowed to do in a classical world. The key difference quantumly is that in a quantum world, I'm going to replace, there's a reason why I wrote an or here, right? I'm going to replace this or over here with an and. Okay? So, first let me just write that in a very naive sense. Quantumly, a quantum bit, or what we will henceforth denote as a qubit, okay, is, well, let me not say is, but can be 0, and 1. Okay, so that's the first major departure from classical mechanics. Okay, so I really want you to think about this for a second, right? If you want, you can pause the video and go into La La Land and imagine what does it mean to say a bit is in two different values at once. Again, I'm not talking about a probabilistic coin flip to say with probably 50% it's 0 and probably 50% it's 1. No, I really mean that your bit is both at the same time. So, the example I like to use is, typically on something like, if I have this pen over here, it's like saying this pen is, on my right side and on my left side at the same time. Or another example I like to use is, it's like you sitting here watching this video and you being out, riding your bike somewhere at the same time, right? That's what quantum mechanics predicts as possible, at least if you interpret it literally, okay? And this is one of the main reasons why it's so counterintuitive. Like, it makes no sense, right? I mean, in your everyday life, you can't do these kinds of things, Shut up. It's a shame, right? If only you could. Okay. So that's a basic principle. It's very, very deep. I just said, okay, 0 and 1, but it's actually a very, very deep idea. So I do encourage you to think about it, next time you're walking around and you want something to muse about. But let's formalize this phenomenon. What does it mean mathematically to talk about, something being in 0 and 1? Okay. So what we'll do is we'll start by encoding classical bits in the standard basis for C2. So encode classical bits, bit 0 as ket 0, which remember was just the standard basis vector 1, 0, and the bit 1 as 0, 1. Right? So these are just the basis vectors we learned about last week. Again, this is exactly why we learned about linear algebra. And now to denote this idea of 0 and 1, all we do is we basically add the vectors. Okay, and addition makes complete sense now because now I'm working over this vector space, C2, right? So we denote a superposition. Maybe I should write that in blue. Zero and 1. Okay, so this is basically my and, the plus. That's how we formally model it. I mean, that's how it turns out, nature works. It turns out you can use this language to describe it. Okay, so when I put this plus, it denotes a so-called superposition of 0 and 1. Okay, and this is completely well defined. This is just some vector in C2. And of course, I might want to think about how much weight is on the 0 versus the 1. You can do this too, right? And so what I can do is I could put weights in front, alpha and beta. Alpha and beta are both going to be complex numbers. And the only stipulation I really will require here, typically we'll use Greek letters to denote quantum states. The only stipulation here is that this thing needs to be a unit vector. Okay, so, and the unit vector constraint, if you plug it in here, you'll see that this means that alpha squared plus beta squared, absolute value, those are complex, is equal to 1. Okay? And the short and the long of it is that any unit vector in C2 describes a valid quantum state of a single qubit. Okay, that's it. So accept that. We're not going to discuss, why that's true or what that's supposed to mean. Tough. Okay, just deal with it. These are the rules we're going to use. Fancy names. These alphas and this beta over here. So this guy here and this guy here. These guys are what we call amplitudes. Okay. Okay, so let me give you an example. So the first example exercise in the notes is a commonly used single qubit state, which is the plus state. Okay, so in this course, whenever you see plus, and also in the literature, it's basically an equal superposition of 0 and 1. And the corresponding partner state, if you will, is the minus state. And that's what happens when we just flip the plus in the middle to a minus. Okay, so now I have a minus in between these two. Okay, so notice that both of these are in C2. Okay, and you might be wondering why I put this funny 1 over root 2 normalization instead of a half, and it's just basically because this makes sure that this is a unit vector. The square root is important. Okay, so remember that to determine the norm of a vector, what you do is you take the inner product with the vector with itself, right? And then you take the square root. And the inner product of the vector with itself will end up giving me the square root of 2 squared, basically. So I'll get a half. Okay, so both of these states, in some sense, are kind of antipodal, if you will, to classical basis states 0 and 1, right? It's like an equal superposition of 0 and 1. It's as far from classical as you can be in some rough sense. Okay. Now, before I move on, let me just make a very brief note about Schrödinger's cat, which is also in the notes. So, you know, we'd be remiss to talk about quantum mechanics and not talk about arguably one of the most famous thought experiments regarding quantum mechanics. This is from 1935. And the idea here is that, you know, Evan Schrödinger came up with this so-called thought experiment involving cats to really demonstrate how silly the idea of superposition is, right? If we were trying to interpret it literally. Okay, so how does this basically work? Let me just sketch it. In this experiment, you take a cat. Okay, clearly I'm really bad at this. Again, I did not choose art as my major, so there's your cat. I'm not sure what that really looks like. Okay, and we take the cat and we put it in a box. And, you know, I really want to make sure it's clear that this box is closed. Okay, so you cannot look inside it. I'll draw a double border. And the other thing that's inside this box is going to be a vial of poison. So I'll draw this as this beaker here that's got this stuff in it. And there's a hammer. Okay, here's a hammer. And the hammer is controlled by some sort of mechanism here, right? It's connected to some sort of computer, let's say. Here's my very advanced drawing of a computer. Okay. And the thought experiment goes as follows. So this computer, the way it works is that if I input, it can take in 1 bit and it will take an action. So if I input the state 0, then nothing will happen. The computer does absolutely nothing. Life is good, right? The cat just continues walking around this little box. But if I put in a 1, then what happens is that the computer will make this hammer drop. So the hammer drops inside the box. Okay, and when it drops, it falls on this vial of poison, and the vial of poison breaks. Right, so poison is released. Okay, and you can guess where this lovely story is going. The cat dies. Okay, so these are 2 options that can take place in the classical world. But I just told you that quantumly we can put things in superposition, right? I mean, you don't have to be 0, you don't have to be 1, you could be both, right? So quantumly, the question is, what happens if the input is 0 plus 1, right? If you think about this literally, right, then what it means is that the hammer at the same time falls and doesn't fall, the flask of poison breaks and doesn't break, the cat dies and doesn't die, right, at the same time. And of course, this is ridiculous, right? I mean, we all know from our personal experience that, you know, this kind of thing does not happen, right? So that's what quantum mechanics predicts is possible, and, you know, there is a way to resolve this paradox, and for that we're going to need the 4th postulate of quantum mechanics, for which we're going to have to wait till next week. Okay, so we'll leave this as a kind of a cliffhanger for now. You know, how do you explain this cat being alive and dead at the same time? Let me be clear that there is one stipulation that I stressed over and over again, which is the box is closed. That's going to play an important role next week. Okay, so for now, just keep this in your head, just, you know, to give you an idea of how ridiculous this idea of superposition is if we try to interpret it literally. Okay, that's all I want to say about Schrödinger's cat. And just a brief note, so far, you know, I described our superpositions for a single qubit, but of course you could generalize this to larger local dimension D. Okay, so we can generalize to not just C2, but to CD, and then any quantum state then is going to be written without lost generality in this way. So we start at 0 just because the first standard basis vector we label with cat 0, and then we go up to D minus 1. The amplitudes are just going to be some alpha I in the complex numbers. Okay, and again, I'll use I in the bracket notation just to specify a standard basis state. Okay, and that's it. And of course, we need our normalization condition, which is that if I take these guys and sum them all up, I get 1. Okay? All the alpha i's, I already said they're in complex. Okay, so in d dimensions, the same principle holds. Any unit vector in CD is a valid quantum state. Okay, good. So that completes section 1.1, and it completes our discussion of individual quantum systems for the purposes of our discussion so far. Okay, so now we can talk about the second postulate, which is, if I have a quantum state and that's all I have, then it's not very interesting, right? I want to be able to do something to it. In particular, as a computer scientist, I want to apply gates to it, right? So that's what postulate 2 is telling us about. What kind of gates are allowed? So postulate 2, quantum operations. And, later on we'll see that what I'm telling you about now is slightly a lie, in the sense that, I'm talking about so-called pure states right now, which are pure state vectors, just vectors. And the operations I'll tell you about now are unitary matrices. But more generally, one can think about non-rank 1 states, which are mixed states, and we can think about trace-preserving completely positive maps, which generalize the unitary operators. For now, don't worry about that. The truth is that anything you can do in the true, more general formalism of quantum mechanics, which I'm not talking about here, you can always simulate using what I am talking about here, okay, using so-called pure states, state vectors, and unitary operations, which I'm about to describe. Okay, so everything I say is in some sense without loss of generality. Okay, so what kind of operations can I do? Well, I have a vector at my disposal, right? That's my state. And so obviously, what do I do with vectors? I like to multiply them by matrices, right? That's what you do in linear algebra. But nature doesn't allow us to apply just any matrix, right? It turns out that everything we do in nature has to be reversible. And in particular, it has to be multiplication by a very specific type of reversible matrix called a unitary matrix. Okay? So nature says, okay, we could multiply any, we can multiply any state vector psi in CD by a unitary matrix, okay, U. And what is this? Well, this is a linear operator that takes CD to CD, so it's always square. And what is the defining property of a unitary matrix? Well, it's that first it's invertible, but not only is invertible, the inverse is very, very simple. All you do is you take the dagger. All right, so over here, you take this dagger operation. And remember, the dagger is nothing other than you take the transpose of the matrix, and then you take the complex conjugate of each entry entry-wise. Okay? So that's the defining property of being unitary. And it turns out that, once this holds, in fact, the other direction holds as well. Okay, so this is a unitary matrix. As an aside, note that all unitary matrices are normal. So if you're unitary, then it implies that you're also normal. Okay, and remember, normal just meant that U and U dagger commute. The order of multiplication doesn't matter. And remember, this is important because normal matrices are the ones we could we could come up with a spectral decomposition for. We can diagonalize. And so unitary matrices are going to be diagonalizable. Okay. Okay, so, there is something, of course, quite deep about this, which is that this essentially tells us that, at least in principle, quantum mechanics is reversible. Nature is reversible, right? Of course, this is not entirely true, and we'll get to why later when we talk about measurements. In order to kind of reverse a quantum operation, you have to see the whole system, if you will. You have to see a so-called pure state. But let's not go there just now. Okay, but let's start with simple examples of gates. Okay, so I'm going to start talking about single qubit gates, because so far we only know how to describe single qubit systems. Okay, so here's the most common gates on C2. Okay, and these are the so-called Pauli matrices. Okay, so we have Pauli X, Pauli Y, Pauli Z. You know, depending on the source you read, you know, they might put an I in front, but typically in quantum computation, we, at least from the computer science perspective, we write them this way. 0 minus I 0, 1, 0, 0, minus 1. Okay, so these are the three matrices on single qubits we'll be using quite often. And, you know, I'll leave it to you to verify that these matrices are unitary. All you have to do, of course, is just multiply, for example, x by its dagger. And in fact, they're a bit stronger than unitary in the sense that they're in fact self-inverse. Okay, so you don't even have to take the dagger in the sense that the dagger equals to the matrix itself. Okay, so for example, if you look at the X gate, right, if you take the dagger of the X gate, then what do you get? Well, the complex conjugate does nothing, so the transpose is the only thing that's left to do, and that also leaves this matrix invariant. So X is going to be self-inverse if you, of course, believe it's unitary, which you should check. So let's focus on the X gate, however, right? So what is the quantum X gate? Well, we sort of touched on this already last week, but let's see if you can guess what goes in this blank over here. So in order to get a sense of what the X gate does, let's just do this. Okay. And let me remind you that this trick, right? So here's a matrix times a vector, and you want to compute the vector, and you want to see, you know, what does the action of the X gate look like? Remember that, you know, the naive way of doing this is to write out the matrix and write out the vector and do it. The slick way of doing it, which I really encourage you to pick up, is because I'm multiplying here by this standard basis vector, then what that does, remember, is that if I multiply by the first standard basis vector, what it will do is it will rip out the first column, okay, of the matrix X. So I don't even have to think, I don't have to write anything down in terms of the matrix X. I already know what the answer is going to be. And likewise, X times the second basis vector, the standard basis vector, that's going to be the second column of X, which is this guy here. So that's 1, 0. And now if we just write this in ket notation again, you'll notice how this is 1 and this is ket 0. So what have we logically done? We have logically flipped bit 0 to 1 and 1 to 0. Right? So in this sense, X is the Pauli, well, I should say, sorry, quantum NOT gate, right? It acts like a quantum NOT gate. So in this sense, you can certainly encode the classical NOT computation. And of course, we can simulate, in theory, anything you can do classically on a quantum computer as well. Okay, though this is, of course, not a proof of that. Okay. So that's the quantum NOT gate. And now let's just observe something very nice. Right? So like I said in this course, we're going to care a lot about things like eigenvectors and eigenvalues. We're not going to care so much about things like characteristic polynomials, right? I mean, nobody wants to sit here and compute roots of this thing. So a lot of times we can guess eigenvectors of operators just by being clever and observing their action on things, right? And here's a perfect example of that. So up here I described, you only know 4 states so far in this space essentially, right? 0, ket 1, and the plus minus states, right? Which I defined up here, plus and minus. So what I'm about to say obviously will involve the 2 states I haven't written here, which are, let's see what happens on ket plus, right? Well, if I just work out ket plus, sorry, x plus, it's what? Well, let's just expand this out. Okay, it's this thing. And these operators are linear, so I could just move everything in. Okay, and now I know exactly how x acts on the standard basis. So we go to 1 over root to 0. And stare at this for a second. Ask yourself, has this state changed? The answer is no, right? This is still the plus state, right? So what do we have? I started with the plus state, I ended with the plus state, times a scalar, of course, which is essentially hiding here. I'm not writing it, but this is just 1 times plus. And so this means that plus is a 1 eigenvector of x. Okay, so eigenvalue 1, plus is the eigenvector. And so again, we just, guessed a good choice of eigenvector just under this observation that, what x does is it just flips 1 and 0. So if 1 and 0 are going to be equally weighted in my superposition, then x is going to act invariantly on this thing. It's just going to move things around. And now let's think about what happens for this one. for the minus state, and I won't work out the full thing. But if you start long enough, you'll probably see that it's going to look just like this case, of course, but when I swap the positions of these two, something will look slightly different, right? The minus sign now is on the wrong spot. And indeed, what's going to happen is that you'll end up getting minus coming out. So let me be a bit more clear. You'll get minus 1 times the minus state, if you work it out. Okay, so what this means is that minus is a minus 1 eigenvector of X. Okay. And can we have more eigenvectors for X? No, right? X is acting on a two-dimensional space. And remember we said last lecture that the eigenvectors for normal matrices, and in particular unitary matrices, can be taken without loss generality to be an orthonormal basis for the space. So I can only have two orthonormal vectors. And in this case, they're plus and minus. We should be a bit careful in the sense that because the eigenvectors here are distinct, so let me make a note here, which might come up later. So if the eigenvalues are distinct, as they are in this case, this implies that the eigenbasis, or the eigenvectors, are unique. So in this particular case, 1 and minus 1 are distinct, so plus minus are the unique eigenvectors of X. You cannot have any other eigenvectors. More generally, if you have eigenvalues which are so-called degenerate, meaning an eigenvalue shows up twice, let's say, then the eigenbasis is not unique. And let's do an example of that. Okay, very naughty example. Are not distinct. But I'm mentioning this now because we're going to use this example over and over again, actually. So if the eigenvalues are not distinct, then the eigenbasis is not unique. Okay, so for example, let's suppose you have in C2, if your eigenvalues are not distinct, right? A natural example of this is the identity, right? The identity as a linear operator in C2, right? Any vector, doesn't matter which one, by definition, for all psi in C2, the identity times psi is just equal to 1 times psi, right? It doesn't do anything. Okay, so all eigenvectors, all vectors are eigenvectors of the identity with eigenvalue 1. Okay, and so, you know, the identity matrix, of course, looks like this. So from last class, you know that this is an upper triangular, well, diagonal matrix, so the eigenvalues are sitting on the diagonal. So you see that 1 is repeated. There are two, there's the same eigenvalue twice, and so that means that in the span of this space, basically, any vector becomes an eigenvector, right? So in this case, what this means is that the identity is diagonalized, not by a unique basis, as was the case for X. X is only diagonalized in one basis, which is the plus-minus basis. The identity is diagonalized in any basis for C2, okay? So in particular, what that means is that I could always write, and this fact I'll use over and over again, I can write the identity just simply as psi, psi, plus psi perp, for all psi in C2, which is unit vectors, of course, here. This is important. And psi perp is just orthogonal to psi. Okay, we're in C2, so up to scaling, there's always a unique orthogonal state. Okay, so the spectral decomposition of the identity is certainly not unique. Okay, and that's because it's degenerate. It has the same eigenvalue twice. And now let's just quickly return to X. Okay, so I know the eigenvectors and eigenvalues of X up here. So now this means that I could write down the spectral decomposition of X, right? I just guessed it, basically, right? So it's plus plus, and remember the eigenvalue here was 1, so I don't really need to include that. But it's minus 1 times minus minus. Okay, so this is a completely different way to write down X that doesn't require me to write out the matrix. And sometimes it's more useful to think about X this way. Okay, so that's the X gate. The other one I want to briefly mention is the Zed gate, right? Pauli Z, which is this guy over here. So, you know, X has a classical analog, it's like a NOT gate, but Z does not have a classical analog. It's a so-called phase gate. Okay? So maybe I'll move this up. So here's the Pauli Z gate. Okay. And in the Pauli Z gate, what does this do? It allows us to inject a relative phase into our quantum state. So let me double check. Sorry, not double check, but let me give you an example. So first, let's just check what Z does on the standard basis, right? And remember, let me just write Z onto the right here. Okay, so that's Z. And so what does it do? Remember, now you should just be able to read this off, right? Multiplying by the first standard basis vector, so it extracts the first column. So this just goes back to 0. Now the second column is basically ket 1, but now there's a minus sign in front, right? So it's minus 1. Okay, so as far as the standard basis goes, the Z vector just puts a minus 1 in front of the ket 1 vector. Okay, it does nothing to 0. And this will turn out to be something called the global phase, which I'll say more about in a second. We can't really detect this minus 1 in this sense, but we can detect it in the following sense. Okay? If I apply Z to a more clever choice of state, a genuinely quantum state, right, the plus state, then what is this equal to? Well, if we expand this out, this is just 1 over root 2 Z0, 1 over root 2 Z1, right? And now I know the action of Z on a basis, on the standard basis. So I could just write out the definition, right? I'm just using these equations on the left. That's 0 minus 1. Okay, so take a moment, stare at this. You know, what state is this? This is now the minus state, right? So that's interesting, right? I started with the plus state, and applying Z to it went to the minus state. So what have we essentially done? I mean, we already have a quantum NOT gate, right? The NOT gate takes us from 0 to 1, ket 0 to ket 1. But if I'm not in the 0, 1 basis, if I'm in the plus minus basis, which is also an orthonormal basis, the correct choice of NOT gate in this basis is actually the Z gate. Okay, the Z gate acts like a logical NOT gate. It takes the plus state to the minus state. Okay, and if you apply it twice, you'll see that it takes the minus back to the plus state, which I won't do here. Okay, so Z is a NOT gate, but now in the plus minus basis. Well, okay, let me be slightly more precise here in my notation. That slash is absolutely meaningless. Okay, we have a set of vectors, they're orthonormal. Okay. Okay, and in particular, there's a special name we give to now this minus, right? So this used to be a plus over here. Over here, I used to have a plus, and when I applied the Z gate, I got a minus, right? And so this is what we call a relative phase, and that's an important term. So a relative phase is basically, you know, a phase at some number on the unit circle. So let's say e to the I theta. So in particular, you know, what's minus 1 on the unit circle? Remember, minus 1 on the unit circle is e to the I pi, because it takes you 180 degrees about the unit circle. Okay, so I have a phase in here, a minus term. Okay, and notice the phase, of course, is not talking about the actual magnitude of the amplitude 1 over root 2. It just cares about, you know, the phase, the e to the I theta term. And it's a relative phase because I can't factor it out of the whole expression. Okay, so of course I could factor out e to the I theta, but if I did that, then, I could factor out minus 1 if I wanted to, right? But then I would have a minus 1 over here, right? So if I wanted to, I could write, you know, z plus, which equals to minus, right? If I want to, I could also write it like this, right? I could factor out the minus term, so I get a plus in the middle now, right? But this is still not the plus state, right? I mean, now I have a minus here instead. So I cannot really get rid of this minus sign in some sense, and that's why it's called a relative phase. But a phase that I could remove from the entire state, I could factor from the full state, that's going to be called a global phase, right? So for example, if I were to take minus the plus state, right, that's minus 1 over root 2, 0, minus 1 over root 2, 1, right? I mean, the way I've written it, right, you could just literally factor out this minus. You just take it, the whole thing comes out, right? And I have some unit vector, the plus state here. And so in this case, we will call this a global phase, okay, because I can factor it out. Okay, so the notions of relative and global phase will be important. The key thing you need to keep in mind is that a global phase, for all intents and purposes, is meaningless. We cannot detect it in experiment. And we'll see why in a second, sorry, not in a second, but in a week when we get to postulate 4 on measurement. We'll see that the mathematics behind measurement will just kill off this global phase. But a relative phase like this can make all the difference in the world. Okay, so in fact, things like Grover search use relative phase. They exploit this to get the square root n speed up, which we'll see later in the course. Okay, good. So finally, I want to say a last gate on a single qubit, which is very important, which is the so-called Hadamard gate. Hadamard gate. Okay. And what is this? You can think of this as kind of the canonical gate. So this is technically the matrix for it. This is the canonical gate that takes us from the classical world into the quantum world. Okay, what I mean by that is that if you work out, let's do one together, right? So what is this? This is 1 over root 2. Okay, sorry, I'm being silly here, right? So what is h times 0? Remember, h is 0 is just going to rip out the first column of h. So what is it going to be? It's going to be the first column of h, which is 1, 1, but multiplied by this normalization factor, right? So what is this thing, right? If you stare at this long enough, you'll see that this is just a plus state, right? It's just ket 0 times 1 over root 2 plus ket 1 times 1 over root 2. So this is just a plus state. And analogously, if you do it with 1, you'll see that it's going to rip out the second column, and that is just a minus state, right? It's 1 and minus 1. Okay, so the Hadamard gate takes us from the standard basis into the plus minus basis, and vice versa. It's also self-inverse, so if you apply it twice, it will undo itself. Okay, so this is one of the basic tools we can use to both create and destroy superposition. Okay, so let me be clear. What do I mean by self-inverse? Let me actually write this down. Whenever I use the word self-inverse, I just mean that h squared equals to identity. So if I apply it twice, it undoes itself. Okay, so in particular, of course, this means that if I do h times plus, if you work it out, you'll see that it'll just take you back to 0. Okay. Okay, so I'll leave you to verify those identities yourself. Let's see, how far are we in? Okay, got it. So let's talk about gates, okay? A lot of times when we talk about quantum circuits, we're going to depict them using the gate model just like you would classically. Okay. So gates, let me say graphical depictions maybe. Okay. So if I have a quantum state psi, okay, whoops, if I'm putting it into a gate, let's say the X gate, the way I depict this graphically is I just draw a box on the X, and I draw this wire that goes through the X gate. Okay, and let's be clear that time goes this way, left to right. Okay, so I could equivalently have written, not equivalently, sorry, but I could have also written, if I want to instead apply a Hadamard gate, I could depict that graphically like this. And of course I could apply both if I like. I could first apply the X gate, and then I can apply the H gate. Okay? So let's be a quick sanity check, okay? This is slightly confusing the first time maybe you do this. This guy here, right, what is this? This is just, I start with my state psi and I apply x, right, for clarity. Here I start with psi and I apply h, Hadamard. And now think about this one. What is this one? Okay, if you first stare at it for a second, you might be tempted to write x, h, right? And, well, this is wrong. Okay, this is wrong. You don't want to do this. Time goes from left to right, right? So the first gate that gets applied is not the Hadamard, it's actually the x gate here, right? So here's x, and then we apply the Hadamard. Okay, so the way we write it in the matrix form is backwards to the way time goes from left to right on these gate circuit diagrams. Okay. So let's do an example. Okay, so it's really that simple. It's just like classical gate circuits. So let's suppose I start in standard basis state 0, and then I apply 3 gates. Hadamard, followed by x, followed by Hadamard. Okay, and the question is, what comes out over here? Okay, and of course, the name of the game here is not to write out the matrices, but to do this just in ket form. Okay, so let's do this, right? So what does this mean? I start with 0, right? And remember, we go backwards to how the diagram is. First I apply Hadamard, which is this first gate here. Then I apply Pauli x. And finally, I apply the last Hadamard. Okay, now let's use the facts that we learned above, which is that, remember, the Hadamard takes you from the standard basis to the plus minus basis. And in particular, it takes the 0 vector to the plus vector. And now I want to remind you that, remember, the eigenvectors of of x were plus minus, right? And in particular, remember, all x does is it just swaps 0 and 1. It flips 0 to 1 and 1 to 0. But this doesn't matter to the plus state. You know, it's only got a plus phase in the middle. So remember that plus is a 1 eigenvector of x. So x times plus is really nothing other than plus itself. Okay? And finally, recall that h is self-inverse. So if I apply h to plus, I take plus back to 0. Okay? So now we see that really this circuit effectively does nothing. Okay? Okay, so again, there's something slightly deep about this, which is that normally, if these Hadamards weren't here, right, flanking this x, the output of this circuit would have been a 1, right? We would have, x is a bit flip, right? But if I first switch to the Hadamard basis and do the x gate, it actually ends up doing nothing. Okay, and intuitively, the reason for this is because just like in the plus minus basis, the correct choice of not gate was actually the z gate. In the plus minus basis, what does the x gate act like? So what's happening here? What's happening here is that, you know, I'm in the standard basis, right? The h effectively rotates me into the plus minus basis, okay, because it sends the basis 0, 1 into the basis, right? So if I have 0, 1, if I have this basis, under the action of the Hadamard gate, it maps me to the plus minus basis. Okay, and there's something very important here, which I'll get to in a second. It maps me to the plus minus basis, and in this basis here, the correct choice of not gate, we noticed, is not x, it's actually z. That will have the logical effect of flipping plus and minus. And the logical z gate, or phase gate, right, to inject minus 1 on 1, is no longer the z gate, it turns out to be the x gate now. It swaps the roles of these two. Okay, so because at this point in the circuit we were in the plus state, which is like a logical 0, the x gate acts like a phase gate on that in this space, so it just takes the plus back to a plus. If it was a minus, x would have then put a minus in front of the state. Okay, just like the z gate would have done in the standard basis. Okay, so if that kind of went over your head, that's fine, don't worry. I mean, this is just slowly getting you warmed up to these discussions. One thing I absolutely want to mention, and I don't think it's in the exercises, but it's absolutely crucial to know this, which is the following. Is it? It might be in the exercises. Which is that a unitary matrix like the Hadamard, one of the beautiful things about it is that it always maps standard bases to standard bases. Okay, orthonormal bases to orthonormal bases. And the reason why is because it preserves length and it preserves inner products. Okay, so a key property of unitary, and I'll let you verify this on your own, unitary matrices map orthonormal bases to orthonormal bases. Okay, so if you start with normal orthonormal basis like 0, 1, and you apply a unitary matrix to this one and this one, the new set of vectors you get is also going to be an orthonormal basis. So in essence, what it's doing is just like a big rotation in space, right? So I had these two vectors, let's say 0 and 1, and a unitary matrix just acts as some funny rotation in space. That's really what it's doing. So it preserves inner products. If these guys were at a right angle, they will remain at a right angle, okay? And their lengths won't change either, okay? And the reason why this holds, of course, is going to be because of the fact that by definition, this property holds, okay? That's what gives you this property, this orthonormal basis to orthonormal basis property. Okay, so it's a nice exercise to prove this. I won't do it here, okay, in the interest of time. Okay, so in this sense, you should always think of unitary matrices as just changes of basis, right? They're just rotating the space. Okay, and that concludes our discussion of postulate 2. Okay, so now let's talk about postulate 3. Okay. Maybe I should give you a quick hint for this, just because I know that if I don't give you a hint, the odds that you'll work on this are probably not that high. But it's nice to see why this property over here is going to be so useful in proving this. So the main thing, of course, you need is, in order to prove that you still have an orthonormal basis, right, you just want to argue that the inner products between any pair of vectors are satisfied, right? So if I start with some psi and phi, for any psi and phi, and then I apply the unitary u to each of those vectors. So I apply u phi, right? That's on one side. And for this one, right, what ends up happening is, of course, I'm sending psi to u psi, right? And here, of course, I'm taking the bra of that. So I have to take psi and I have to take the dagger, u dagger. Okay, because that's the bra. Remember, the bra takes the dagger of everything. Okay, and so here what we will get is u dagger u, right? And, well, u dagger u is just identity, right? So that's just going to disappear. Ta-da, right? So that's literally what we had over here, right? So applying u to both vectors didn't change their inner product. And that's, now this part I really will leave to you. That's enough to guarantee that an orthonormal basis gets mapped to an orthonormal basis. Okay, so that's postulate 2. Let's talk about postulate 3. Okay, so far what we've done is we've talked about, ooh, that is not a good idea. Okay, so far we've talked about postulates 1, 2, how to describe a single quantum system, single qubit, what kind of gates you're allowed to apply on a single qubit. And now, of course, you know, a computer consisting of one qubit is completely uninteresting. We want to compute using multiple qubits at the same time. So the question is, you know, what is the formalism to describe multiple qubits together, right? It's not enough to just take the dimension to be, you know, d as opposed to just 2. This is not the same thing, right? Okay, in some sense, it turns out, yes, that is the same thing, but, you know, that's not... Let me just write down postulate 3 and we'll see where we go, okay? The correct way to do this, the correct mathematical formalism to stitch together the descriptions of two quantum states is via an operation known as the tensor product. Okay, so odds are, you know, linear algebra is a prereq for this course, but the tensor product operation is probably something you haven't seen before. Certainly I hadn't seen it before I learned about quantum mechanics. Okay? So the question is, you know, how to describe the joint state of multiple quantum systems. Okay, and you know, once we can do it for 2, we could generalize to more than 2, of course. Okay, so the answer is something called the tensor product. Okay, it's a special operation that takes in 2 vectors. You could also be matrices if you like, and stitches them together to get one bigger vector. Okay. So how do I want to do this? What it will do is the following, right? It's the tensor product, right? And okay, let me first give you the formal definition, right? So it will take an element. I'm going to work over qubits for now just to keep life simple. Okay. But of course, this dimension 2 could be any dimension you want. And what it's going to, well, okay, let me be a little bit more formal. Actually, I changed my mind. A bit more general, because we're going to actually need that. So let's suppose I have 1 dimension, and I have a 2nd dimension. Okay, so what it does is it takes 2 quantum systems. So this is, you know, system 1, system 2. So it takes in 2 quantum systems, the descriptions of each, and it stitches them together to get a description for the joint system, right? And now the question is, you know, what space does the joint system live in? And, you know, in a very nice ideal world, what I would write here is d1 plus d2, so that the dimension grows linearly. So if I can describe, you know, each of these guys separately, I can certainly describe them together. Unfortunately, nature hates us a little bit because that's not the way it works at all. It turns out that nature is not our friend. The correct formula is not d1 plus d2, but it's d1 times d2. Okay, so this essentially means that if I start stitching together quantum states, right, or quantum systems, the size of my Hilbert space, my dimension here, grows multiplicatively. So, you know, if each of these were just a single qubit, they're 2, dimension 2, but I stitch together n of them, right, the dimension of my system is going to end up growing exponentially, right? So I'm going to have dimension 2 to the power n. Okay? Ooh, that's not good, right? Sad. Sad emoji, right? Okay, so that's, you know, and that's precisely one of the reasons why, by the way, quantum computing was first proposed by people like such as Richard Feynman, which is that, you know, you can't write down these vectors if I have an n-qubit system. The dimension on this complex space is going to be 2 to the power n. I can't even write that thing down, right, classically. So Richard Feynman, for example, proposed that why don't we just, instead of kind of trying to study these quantum systems by writing them down explicitly, why don't we just build a quantum computer? And maybe that itself could study these systems for us in a more direct fashion. Okay, that was one of the original ideas. Okay. So let me give you the formula. Okay, so far I haven't told you how the tensor product works. The formula is slightly nasty, especially when we start writing it down for matrices, but you know, the easiest way to learn about the tensor product, I think, is just by doing an example. Once you see the example, I think it's pretty straightforward. Okay. Okay, so how do we do this, right? So the entries of, you know, psi tensor phi. So I'm taking the tensor product of 2 vectors. To make life simple for now, I'm just going to assume that these guys are in C2. Okay, so they're qubits. So it can be referenced by a pair of indices. I comma j, and for I and j are in 0, 1. Okay, and so note how, in particular, I'm saying that to reference each entry of this thing, right, over here, to reference each entry of that, you give me a pair of indices from 0, 1, right? So the set of all possible indices is, there are 4 such combinations, right? 0, 0, 0, 1, 1, 0, 1, 1. Okay, and so you already see where the dimension 4 is going to come in now. Okay, and the rule of this is going to be the following, that if I take this guy over here, and I look up entry I comma j, okay, then it's going to equal to psi I times phi j. Sorry, this should be an I. It looks kind of like a j. Okay. Okay, so take the ith component of the first vector and the jth component of the second vector and multiply them out. Okay, and these are just the entries, remember? So, ooh, don't do that. Seriously. Good. These are the entries of, for example, phi. Okay. And so note that there's no star here, right? I haven't taken a complex conjugate because they're both ket vectors. There's no bra here. Okay, and so of course it's a bit cumbersome to carry around, pairs of indices, right? So instead of saying 0, 0, 0, 1, 1, 0, 1, 1, which is counting in binary, I might as well just count in decimal, essentially, right? So in the sense that instead of writing a pair of indices, from now on I'll just write 0 up to 3 instead, okay? So, so typically, instead we just write psi tensor phi, and now I'll just use one index of I, let's say. Well, okay. This is not very much fun. Let me not do it that way. It's a bit annoying, but suffice it to say we're just going to index this vector in decimal, okay? So let's just do an example just to keep our life simple, okay? And let me be clear that, there will be 4 such entries because there are 4 choices of pairs ij. So let's do an example. Okay, so let's suppose I start with ket 0 and ket 0, right? Then what is that? That's just 1, 0, tensor 1, 0. Okay? And how do you work this out? Well, if you want, you could stare at this formula, but there's a much easier intuitive way to do this, which is that all the tensor product does is it just takes the first vector, all right? So let me take the first vector. Here's my 1, here's my 0, that's this bad boy over here, okay? And it basically squishes in a copy of the second vector at each coordinate. Okay, so it multiplies by a copy of the second vector, 1, 0. Okay, and the reason why I'm showing you this view is because when we do it for matrices, this is a much nicer way to think about it. So here's my second copy, that's this guy here, and that's this one over here, okay? And so what is this? Let's just multiply out now, right? Over here, I've got 1 times 1, 0, so I'm just going to get literally 1, 0 now at the top. And at the bottom, I have got 0 times this, which is just going to be 0. Okay, and you'll notice now that this vector is in C4. Ta-da! Okay. Okay, and so likewise, if you work out 0 tensor 1, you'll see what is this? Well, it's going to be 1, 0 tensor 0, 1 by definition, right? And what is that? I'm just going to do this now in one step. It's the same process, right? You do 1 times this vector, right? So that's just 0, 1. And then you do 0 times this vector, which is just 0, 0. Okay? And I'm not going to do it here, but let me leave it as an exercise for you to try out yourself, that if I do 1, 0, I'll get 0, 0, 1, 0. And if I do 1 tensor 1, I'll get 0, 0, 0, 1. Okay? And now I want you to stare at these 4 vectors I got for a second, right? I got this one, and I got this one, and this one, and this one, right? So what is this? Where have you seen this before? So this is just the standard basis for C4, right? That's all it is, right? This is just the standard basis for C4. And so, let me do it in green. So here, 1, 2, 3, 4. That's the standard basis for C4. And normally what we were doing is we were labeling the standard basis for C4 like this, right? 0, 1, 2, and 3, right? And instead, the labels here now are essentially in binary, right? It's 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 1, 2, 3 in decimal. So the notation works out really, really nicely here. Okay, so this is also one of the reasons why I really like the Dirac notation for dealing with this. Again, no offense to the haters out there who are not big fans. Okay, so, and this will be one of the exercises on A2, which is that in particular, this is not a coincidence. What happened is that I took a pair of orthonormal bases. I took 0 and 0, 1 on this qubit and 0, 1 on this qubit. So by the way, this is like, we think of this as qubit 1 and this one here is qubit 2. I took a pair of orthonormal bases, right? And then I stitched them together using the tensor product, right? And the four combinations that came out, 0, 0, 0, 1, 1, 0, 1, 1, that itself is a new orthonormal basis. And so it turns out this is a fact, right? So tensor products map orthonormal bases to orthonormal bases. Okay, so this is on your A2, I believe. Okay, so in particular, if I take the tensor product of the standard basis on a pair of quantum systems, that's going to give me the new standard basis on the bigger joint quantum system. Okay, so that is a very important fact to keep in mind. Okay, so maybe I'll be a little bit more precise in this statement. So if I have orthonormal bases, psi 0, psi 1, so they don't have to be the standard bases, they can be anything. Phi 0, phi 1. Okay, so each set here is an orthonormal basis. Then it implies that if I take the pairwise tensor product of all possible combinations, so psi 0, tensor phi 1, psi 1, tensor phi 2, psi 0, tensor phi 0, psi 0, tensor phi 1. It's morning, you'd think I would have a lot of energy, but somehow that didn't quite work out, I guess. Psi 1, tensor phi 0, psi 1, tensor phi 1. Okay? So this is also an orthonormal basis. Okay, and so, if these guys were C2 in this example, then this is going to be an orthonormal basis for C4. Okay, so just like we saw with the standard basis here. So that's on A2, you can prove that. Fun stuff. Okay, and of course, if we were to write this funny X-Men symbol, this tensor product, right, over and over again, every time we needed to write down quantum states, it's going to drive us crazy. So what we normally do is we just omit the tensor product symbol. Okay, and what we instead write is, instead of writing psi tensor phi, we just write psi phi. Oh, sorry, psi phi like this. Okay, so we just write them side by side, and that implicitly denotes there's a tensor product there. If we're dealing with standard basis states, we go a step further, right? Because we had this really, well, let's not do that. Because we had this really nice effect here, right? That tensoring, for example, 0, 0 together gave us, the first standard basis vector on C4, which should be labeled by the bit string 0, 0. It makes sense to just replace this thing here. So not just write it as 0, 0. We could do that, but let's go a step further and just write it as just 0, 0 like this. Okay? And so that notationally will be 0 tensor 0, ket 0 tensor 0. So in particular, if I have, I tensor j for standard basis states, okay, typically I'll just end up writing it as ij. Okay, and this is standard in the field. Okay, and this allows us to now reference these higher dimensional states by, the bit string ij, which is very useful. Okay, so maybe let's do a quick example, because we won't have tutorials for this, the first or the second lecture. Let's just do, just to make sure as a sanity check, let's do this. Okay, so 1 tensor psi. What is this equal to? Okay, so there are two ways to do it. Because I haven't told you the rules of playing with the tensor product yet, which I'll do in a second, let's first do the matrix way, which is to say, let's write out the matrices. I know this is taboo in this course, but There are exceptions to every rule. This is one of them. Okay. Okay, so what did we do? Remember, the rule was that, first this is going to be a 4-dimensional vector. Okay. And again, what we do is we take this number times this vector, which is just 0. It's a 0 vector. And then we take this number here times this vector, which is going to be 1 over root 2, 1, 1 over root 2, minus 1. Okay, and of course what I could do is I could just factor out the 1 over root 2 if I like, and just write it as 0, 0, 1, minus 1. Okay? Okay, what is the other way of writing this that I haven't really told you about yet, which we'll do now, but if we want to, we could use just ket notation. Ideally, that's what we would do, right? Okay, so we just write this out. And what I haven't told you yet is that the tensor product is distributive. Okay, so I could just move it in a very nice way. It turns out that this just equals to 1 over root 2. It basically acts exactly the way you would expect it to act, right, for a product, basically. This is this, minus 1 over root 2, 1, tensor 1, right? And remember, let me just slowly start getting you guys used to this. I'm going to contract these two together to make the indexing nicer. Okay, and what is this? Let's just write it out. All right, this is 1 over root 2 times the third basis vector, standard basis vector for C4, so that one. And the second term is 1 over root 2 times the last standard basis vector for C4, because it's labeled 1, 1. Okay, and if you just stare at this long enough, you'll see that this is really just equal to this. Okay. Ta-da! Okay, so that's how the tensor product works. Again, the formula in terms of like indexes can be quite cumbersome. Like, where was that thing? I don't even want to look at it. Anyway, yeah, this thing, right? So that can be quite cumbersome, but the intuitive rule for how to apply it is very straightforward. Just takes a bit of practice. Okay, good. So before I write down the rules for how the tensor product works, let's just make an observation or a note or a fact, let's say, that everything I've said about the tensor product applies straightforwardly, generalizes to higher dimensions. Okay, so all of this generalizes to if I have CD1 tensor CD2. Okay, so in particular, what this means is that if I have psi in CD1, phi in CD2, okay, then I have a pair of indices, right? Now, the indices now, it's important that I have two different indices in this regard, because now, of course, the dimensions of the input spaces don't match, right? I have CD1 here, and this is a different dimension, D2. So the indices now will reflect that, right? The first index, which comes from the first system. Again, we think of this as the first system, and this is the second system. So the index of the first system goes from 0 up to, D1. And the second index, of course, will index the second system. So it depends on D2, right? So, if this is a much larger dimensional system and this is just a qubit, this one can take on a lot more values. So what we have now is just like before. If I have psi tensor phi of I comma j, right? What is that? Well, that's just equal to psi I tensor phi j. Okay, like zero surprises here. Okay. So here are the rules of playing with the X-Men. Okay, again, I could swear this is the X-Men symbol. That's why I like to say that. For playing with the tensor product, right? If you're bored, you have nothing to do, you want to play with something, tensor product. So I'm just going to write down a bunch of rules. This is going to be boring, but you need to, well, most of these rules are expected, right? In terms of a product, the way, you're used to the multiplication working. But some of them will be slightly not obvious and will be very, very important. Okay, so we do need to write these down at least once in the course. So here they are. The first one is going to be distributive. Well, this is from the left, from the right. So Okay, so A tensor C plus B tensor C. Okay, so that's one. You get the same thing from the left, meaning if you have A tensor B plus C, doesn't really matter. This is A tensor V plus A tensor C. Okay, so multiplication by scalars. So this is, again, just as you would expect. If I have a constant times a tensor product, the C being the constant here. This is a constant, oops, constant, okay. Then this is just going to be equal to C times A, tensor C, or if you want, you can move to the constant to the second half. It doesn't matter, but you can't put it in both. I mean, you have to pick one, and then if you want, you could put it there, okay. Okay, so an important one, which is not entirely obvious, which is that if I take A tensor C, right, and then I take a dagger, right, the dagger acts individually on each of the subsystems. Okay, so then I get A tensor C. So, the ket A goes to bra A, ket C goes to bra C, and so the entire ket vector here goes to a bra vector. Okay, and so once I have that at my disposal, I can tell you how to work with tensor products in this, or how tensor products play with this notation. Okay, so the tensor product, so the inner product, sorry, of two tensor products is, it's going to work very nice. It's going to preserve the quantum systems in the sense that, in this picture, right, this is quantum system 1, this is quantum system 2, this is quantum system 1, this is quantum system 2, right? So let me just be precise. I remember when I was first learning about these things myself, it was a bit confusing because it wasn't clear what was which system. So let's be very clear. Sorry, I should not be doing that. Okay, so let's be clear here. What did I want to do? Oh yeah, so this is just equals to what? It's A times B, right? So that's the first system term, right? So there's system 1, so those guys get paired together. And at the same time, C and D get paired together. Okay, 1 and 2. Okay, and so notice how this term here is in the complex numbers. It's a scalar now, and this term is also a scalar. And so, of course, the entire thing is also in the complex numbers. Just one scalar times another. That's exactly what you expect out of the inner product. Okay, so let's do a quick example. So what is the inner product, say, of 0, what do I want to do here? Let's say 0, 1, okay, and then tensor with, say, plus and minus. Okay, so what is this inner product? So the rules of the tensor product state that we're going to put system 1 will go together and system 2 will go together. It's going to preserve the systems in that sense. So you get inner product of 0 and plus, that's the first system, times the inner product of 1 and minus, right? And so what are each of these things? Well, the inner product of 0 and plus, I mean, maybe the first time I'll do it explicitly, right? This is 1 over root 2, 0, plus 1 over root 2, 1. Okay, and then, sorry, not a plus, but now I have a multiplication, right? And then times, this is going to be 1 times 1 over root 2, 0, minus 1 over root 2, 1. Okay? And so when you multiply this out, this is an orthonormal basis, so what you'll get is 1 over root 2, just from this term here, that's this term. And from this term, you'll get almost the same thing, the 1 and the 1, the 1 and the 1 here, so this one and this one will go together, and you'll get minus 1 over root 2. Right? So you get minus a half. That's your inner product. Okay. Okay. So that tells us about the tensor product, right? And, as I write in the notes here, and what I like to say basically is that, now that we know how to stitch together a pair of quantum systems, there's a sense in which we've opened Pandora's box. Because now it turns out that, we're in a whole other realm of states that are possible for our quantum computer than you could ever hope to get with a classical computer. Okay, and in particular, we're going to give rise, it gives rise to this phenomenon known as entanglement. Okay, so okay, and so what is entanglement? Well, very roughly speaking, before I told you that I could take, if my first qubit was in state 0, maybe I'll put a subscript 1 to indicate this is qubit 1. And my second qubit was in state 0 as well, right? Then, the joint system is described by this tensor product. And, I know the joint system state, but I also know the individual qubit states, right? Individually, qubit 1 is in state 0, and qubit, 2, typo, is in state 0 as well, right? And that's kind of what we know from the classical world, right? That any state, any joint state of two parties, let's say, you have a couple, a pair of people, right? You can always describe, the state of each individual person in that couple, right? But when it comes to entanglement, it turns out in quantum systems, that's not always true. That just because you know what the joint state is, you might not be able to say anything about the individual states anymore, okay? And that is this phenomenon of entanglement. That's one way of saying it, at least, right? So these guys in particular would be what we call unentangled, okay? But here's an example of an entangled state known as the so-called Bell state, okay? And the notation we typically use for this bad boy is phi plus, and I'll write it this way. Okay, so again, I'm omitting the tensor product. Okay, so this is a state, there are two qubits here, right? 0, 0. So again, let me be very clear. This is qubit 1. This is system 1. This here is system 2. And likewise, this is system 1. This here is system 2. Okay? So there are two qubits. This is a state in a vector in C4. And so what does it mean to be able to describe the state of system 1, at least naively? What would you want to do? Well, you would want to kind of factor it out, right? You want to factor it out as far as this vector goes. You want to factor with respect to the tensor product and see that, okay, on system 1, I have this state. So for example, here I can factor with respect to the tensor product because, well, I mean, it's already in factorized form. It's, 0, tensor 0. So locally, it looks just like 0. But if you stare at the state long enough, and you can prove it formally, that this state can never be factorized. Okay? Okay, so let me be very clear. What do I mean by that, right? There do not exist, okay, psi and phi in C2. So there is not a pair of two-dimensional vectors such that when I stitch them together via the tensor product, it equals to phi. Okay? So that is the definition of entanglement. Okay, the formal mathematical definition. Okay, so if I have a pair of pure quantum states, okay, or states that we've described them so far, vectors, the state, such as in this example, phi plus, this is an entangled state if and only if you cannot factorize it in this way. There isn't a pair of constituent states phi and psi and phi, so that their tensor product gives me back phi plus. Okay, so this is what we call entanglement. Okay, and so intuitively, I mean, this is again one of the really, really highly non-trivial things about quantum mechanics. This essentially says that these two qubits in the system are so tightly bound that somehow they don't make sense without each other. Okay, so just locally looking at one tells you nothing. Okay, now of course there is a formalism in which we can at least write some sort of description about system 1 or system 2, okay, separately. But there's a sense in which it will no longer give us all the information anymore. Okay, and we'll get to that when we start talking about density operators. Okay, but for now, certainly in this pure state formalism that we've been using so far, you cannot say anything about the individual subsystems. Okay, And so quantum mechanics, of course, again, this is highly non-intuitive. And this notion of entanglement, in 1935, there's this very famous paper by Einstein, Podolsky, and Rosen. It's usually just abbreviated EPR. Okay, and in this paper, they argued that, the theory of quantum mechanics that had been developed until that point, basically, it could not be complete. Basically, there had to be something missing because essentially of this notion of entanglement. How could you have these two states that are so tightly bound together in this regard? Okay, and now, of course, if you fast forward to, I guess 80 years later now, now we believe that, not only is entanglement an important part of quantum mechanics, right, an unavoidable part of quantum mechanics, but in fact, it's a necessary resource if you want to exponentially outperform classical computers. Okay, so in other words, if you have a computation where the entanglement doesn't grow exponentially with the length of the computation, I'm waving my hands here because I haven't defined what it means to grow, for entanglement to grow here. But then you could simulate such computations classically, it turns out. Okay, so and again, all of this is in the setting of pure states. Okay, so entanglement is important. Let me remark here that there's this vector, the first Bell state, if you will, phi plus, right? But it turns out phi plus is not alone. I'm not sure why it's doing that. It turns out that phi plus is not alone. When it comes to C4, there are three other basis vectors that are all entangled. Okay, and in fact, they're maximally entangled, which I haven't really argued yet. Okay, so phi plus can be completed to a basis for C4, not the standard basis, right? This will be a totally different basis. So there's phi plus. Let me just rewrite it here. 1 over root 2, 0, 0, plus 1, 1. Okay, and then if I put a minus here, you can probably guess where this is going. Same thing, but it will be a minus in the middle. And then we have psi plus and psi minus, which is 0, 1, plus 1, 0. Okay, so we flip one of the qubits. And again, this is the same thing, but with a minus in the middle. Oops, 0, 1. Oops, why did I do it that way? So 0, 1, minus 1, 0. All right. So, and these guys together, there's a special name we give them. These are called the Bell basis. Again, for C4. Okay, 2 qubits. Okay, and just as a point of reference, so of course these are named after the Northern Irish physicist John Bell, who's very famous for his work on things like Bell, what we now call Bell inequalities. Okay. Okay. So I'm not going to verify that the Bell basis is indeed an orthonormal basis, but it is. Okay. So sorry, let me be clear. This is an orthonormal basis. Okay, so a basis need not be orthogonal, nor does it need to be normalized, but of course we like to play with orthonormal bases. Okay, and so now that I've told you about composite quantum systems, we can talk about 2-qubit gates, right? So the more interesting gates. Okay, so these are gates that act on multiple qubits at the same time. Okay, so what are these? Of course, these are just going to be unitary U, and they're going to be linear operators that send C4 back to itself. Okay, so they act on 2 qubits at a time. And there are going to be 2 types of such gates we'll deal with, generally speaking. So type 1 is just going to be a tensor product of single qubit gates, which essentially just means pick your favorite single qubit gates and apply one of them here and one of them here, and that's it, right? There's nothing kind of clever going on here. Okay, so type 1 is basically just tensor products of single qubit gates. Okay, so, examples are, maybe you do an X on qubit 1, a Z on qubit 2. That's a perfect example, right? Or is there anything particular I want to say? No, I mean, if I want, I could do Hadamard's on all my qubits. So Hadamard on qubit 1, Hadamard on qubit 2. Again, to be clear, I'm indexing, 1 for qubit 1, 2 on qubit 2, just to try and be clear, right? And now, of course, I need to define for you formally, I mean, I don't really, but I will define the tensor product on matrices, but the definition is essentially the same as for vectors, and it's even more cumbersome in the matrix notation. The intuition behind it is exactly the same. Okay, but let me just write down the definition for completeness first, and then we'll do the intuition. For any A in CD1, B in CD2, okay. A tensor B is D1, D2 times D1, D2 complex matrix with entries indexed by. So remember that when I put square brackets like this, it means, the numbers from 0 up to d minus 1, the natural numbers from 0 up to d minus 1. So you give me a pair of numbers from those two sets, and you do that again. Okay, so, this is going to give me the row, of course, together. That will give me the row, this two tuple, and now the two tuple I write down will give you the column. Again, I told you this is going to be cumbersome. And yeah, just for completeness, remember this just means the set 0 up to d1 minus 1. So that was notation from the first lecture. So what does this mean, formally speaking? This means that I1 tensor J1, sorry, there's no tensor here. I1 J1, I2 J2. Okay, what is that? Well, that just equals to A of I1, I2, B of J1, J2. Okay, so now that I've taken the time to written down that definition, you can promptly forget about it because it stinks. Let's just do a very simple example to show you that this is exactly the same as the tensor product on vectors. Okay, so just like before, we're going to do the same thing, which is that, suppose I want to take the tensor product of these two matrices. I'm going to do the exact same thing. I'm going to take, first of all, it's going to be bigger, right? So these are 2 by 2. So the joint matrix will now be bigger. It will be 4 by 4. Okay. And what we're going to do is just like before, just like for vectors, I'm going to take A1, A2, A3, and A4, just like before, right? And these all come from the original matrix, right? Or the first matrix. And at each of these coordinates, I insert a copy of the second matrix, just like before. So B1, B2, B3, B4. Okay, B1, B2, B3, B4. And that's it, okay? And now if you stare at this, you'll see that the resulting matrix you get will indeed be 4 by 4. Okay, and I'm not going to write out the full thing, but you can start writing out some of the terms. So in the top left corner of this thing, the top 4 entries of it will be what? It will be A1, B1, A1, B2, A1, B3, A1, B4. Right, and that's the top left block. And I'll let you fill in the rest. Okay. So ... Okay, so again, the technical formula is just a convoluted mess, but the intuition is quite simple. Okay, so let's do an example. Let's make sure we get this, all right? Sanity check. So the example is going to be Let's do X tensor identity maybe. So what does X tensor identity look like? Well, remember the X operator is quantum NOT gate. The identity looks like this, right? So as a matrix, the way this looks is, remember what we say is it's the same thing, right? We take 0 times the identity basically on the top left, 1 times the identity on the top right, 1 times the identity here, 0 times the identity here, okay? And if you like, you can think of this as a block matrix. Okay, and so that just basically means what? It looks like 0 on the top left. Here I have a copy of the identity sitting here, another copy of the identity, and all zeros. Okay, so that's X tensor identity, for example, and you could do this for any matrix you like. Okay, so so properties of the matrix tensor product. Okay, so these are basically the same as for the vector tensor product, but so same as the, let me put it in quotes, the vector tensor product, plus two other nice things which are good to know. Okay, so A tensor B and C tensor D. Again, this is just like the inner product formula. I mean, it's essentially the same property, right? Which is that, again, think of this as these are both system 1. These are both operators acting on system 1. And here I have system 2. And what we do is, those systems, play with each other basically, meaning A plays with C on system 1, and B and D stay on system 2. Okay, and intuitively this is exactly what you want, right? Because what this is telling you is that if I'm doing this unitary, A on system 1 and a C on system 1, I mean, so first you would apply C, then the A, right? Then together the joint action should look like first C and then A getting applied. Okay. So this, let me just point that out. And the other one that's really nice to know is this trace formula, right? If you have the trace of A tensor B, you can work this out, that it's really just a product of the traces. Okay, and how would you prove this? So whenever you try and prove anything in quantum information, the first thing you should always try is spectral decomposition. That's one way you can try and prove this. Okay. So take spectral decompositions of A and B and just verify this formula. Okay. So let's just see this property in action. So if I have, for example, y tensor y, right? I apply y on qubit 1, y on qubit 2, and then I do this again. Well, let me do something like this just for fun. Okay, so what is this equal to? Well, this is just going to be y1 times y1 on qubit 1, right? Sorry, I should maybe not write it this way. Okay, this is going to be y all on qubit 1, tensor, yz on qubit 2, right? And remember we said that the y operator is self-inverse. Okay, so it's not only unitary, but if I square it, I just get the identity back. So I get identity on 1. And on 2, well, technically speaking, I have y times z. And, if you actually work this out, you'll find that this y times z will just give you x back. Okay, a Pauli x up to a scalar in front. More accurately, a phase on the unit circle. Okay. And so how do we depict these things via circuit diagrams? Right, that's important. What does it mean to put this tensor product for gates, circuit diagrams? Okay, so for example, I'm just going to do by example. I think that's easiest. X tensor identity. What does the circuit diagram for that look like? Identity tensor X. And let's do another one, H tensor H. So now I have two qubits, right? There are two systems here. There's one system and a second system, right? And so I have to have two wires. So here's qubit 1, here's qubit 2. This is qubit 1, this is qubit 2. Okay? And what do I do? Well, this says that on qubit 1, we're going to apply the X gate, so I'm going to put an X here. And this says that on qubit 2, I'm going to apply an identity gate, or do nothing, basically. Okay? That's the circuit. And you'll notice that the two wires, of course, do not touch each other. They don't interact because the gates are really single qubit gates. even though, you know, I've written it as a 2-qubit gate, as an operator on C4. Okay, so how about this one? Same idea, of course. Now we just swap the order of the wires because the way I've specified it, the identity now acts on qubit 1. And now we can do the same thing here, except, you know, we can do Hadamard's on each qubit. Okay, so circuit diagrams are very, very straightforward. Okay, so let's just do a quick sanity check just to make sure you're comfortable with the notation. So what happens, for example, if I do this? Z tensor Z, right, on 1 tensor 1. Okay? So first let's do it algebraically, right? Algebraically, remember this means what? It's just, you know, Z, this first Z is acting on the first system, right? And the second Z is acting on the second system. All right, so let's just write it that way. So this, there you go. For first system here, right? Second system here. And remember what we said is that when Z acts on ket 1, it kicks out a phase of -1. Okay, but now I have 2 copies of this phase, right? I've got 2 copies of this -1 phase floating around. They're going to cancel, right? So really this just leaves me invariant. Okay, so as an aside, what we've just shown essentially that 1, 1 is a 1 eigenvector of Z tensor Z. Okay. By the way, it is not a good idea to drop, so I drop tensor products here, right, on states, because there it's fairly clear what we mean. It is not, generally speaking, a good idea to drop the tensor product between the, you know, operators, because these, you know, unless you're a physicist, in which case you love to do this, but, you know, it drives me crazy, because of course these two things have 2 very, very different meanings, unless of course you're labeling your systems, right? So right now, the way I've written this, you know, the natural way to interpret this is that, you know, I have a Z acting on a 1 and a Z acting on 2, qubit 1 and 2. This just looks like Z squared, which is the identity. So of course, you know, a good way around this is to just label these qubits to be clear that, you know, this is not really a product on the same system. So this is really an implicit tensor product. So, but in this course, we will be good boys and girls. We will always write tensor products for gates. Okay, so that's the first type of gate. And there's a sense in which that's less interesting. The really interesting type of gate is the type of gate that cannot be written as a tensor product of individual single qubit gates. Okay, so maybe these are what I'll call genuine 2-qubit gates. Okay, and what do I mean by that? These basically cannot be written as tensor product, and the kind of canonical example for this is this control NOT gate. Or just C0. Okay, and this thing, it's going to be acting on C4, right? Map C4 to itself, so I need to write down a 4x4 matrix. Okay, so what does this matrix look like? First, let me write it in block form, because that's the easiest, right? So you have a 2x2 identity in the top left, and the Pauli matrix in the bottom right. Okay? And then if I expand it out and just write it out fully, I'll just look like this. This is just 0, this is just 0. And now here's your X gate. Okay, so that's what the C0 matrix actually looks like. But it's a lot more interesting. I mean, you could extract this now from the description I've written down, but most importantly, let's write down the action of C0 on a basis. And the basis which is most important to really understand this action is actually the standard basis. So action on a basis. Sorry, one sec. Okay. So it's action on a basis, on the standard basis more accurately. Okay, this action is going to be what? Well, okay, C0. And now you have to be a bit careful, okay, because we're going to have to specify, there are 2 qubits, each of one's going to play a role, right? So first, maybe I should draw the circuit diagram first. So the C0 we normally write like this. Okay, so this is the C0 gate I'm drawing. So this thing here, we normally don't draw a box around it. And so the reason why you have a different picture on each qubit is because each of them plays a different role. So the top qubit here, the way I've drawn it, wherever the black dot is, that's the control. Right? That's the control qubit. And the one where this crosshair is, that's the target qubit. Okay, and the idea is that it's a controlled knot. So it's going to apply a knot on the target qubit, but only if the control is set to 1. If the control is 0, nothing will happen. Okay, so in particular, what we'll see, well, maybe I shouldn't write it this way. What is its action? So what it's going to do is 0, 0. What's going to happen under the C0? It's going to get mapped to, well, just 0, 0. So again, I'm going to think of these as 1 and 2, okay? So this is qubit 1, this is qubit 2, this is qubit 1, this is qubit 2. Let me be clear, okay? So if your control qubit is set to 0, nothing happens. Likewise, if I had 0, 1 here, again, nothing happens because my control qubit is set to 0. But if my control qubit is set to 1, like in this case, then it flips the second bit. It just does an X gate. And likewise, sorry, shouldn't have happened. Likewise, over here, this should go to 1, 0. Okay, so that's the action of the C0. And I started by giving you the matrix description, but of course from this we could very easily recover the matrix description, right? The matrix for the C0 is what? Remember, how did we do this? We just write down the columns, which are the action on the standard basis. So the first column is just 0, 0, right? The second column is just 1, 1. Yeah. The second column is just, 1, 1, right? That doesn't look right to me at all. Oh, that's because I swapped the order of the basis, right? Okay, sorry. So normally we would write it in this order, right? So clearly I don't know how to count in binary. So 0, 1 should get mapped to over here. So let's do this one. 0, 1 gets mapped to 0, 1. So the next column will be 0, 1. In the third column, we're supposed to see what happens to the third basis vector 1, 0, and that's 1, 1. Okay, and in the last column, we're supposed to put down what happens to the last base vector, which is 1, 0. Right? And what is this? Well, the first guy is just 0, 0, 0, right? The second one is just 0, 1, 0, 0. So far, we've reproduced exactly this, so that's perfect. And then you get the last two columns, which look like this, right? And that's exactly what I wrote up here. Oops, let me just move that down a bit. Yeah, that's exactly what I wrote up there. Okay, so again, once I know the action on a basis, in particular the standard basis for this example, I could reconstruct the matrix from scratch. Okay, so very, very good. So the C0, this is how it acts on the standard basis, but of course what's interesting for us is how it acts on entangled states. So let's do that. So let's do an example. What does the C0 do? And I'm going to write 1, 2 here. Then the convention in this course is that if I write 1, 2, I always mean whatever I list first is going to be the control qubit, and whatever I list second will be the target qubit. Oops. So this is going to be my convention in this course. Okay, so if I apply this to the Bell state, phi plus, which remember acts on 2 qubits, 1 and 2, what does it do? Well, the best way to see this is just, again, we just expand the definition, right? 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. We use the fact that all these operators are linear, so I can move the C0 in. So I get C0 of 0, 0, plus C0 of 1, 1. Okay, and what is this? Well, we know the action now on a basis, right? So I expanded it in terms of that basis. C0 of 0, 0 just leaves the state invariant, right? But C0 of 1, 1, what does that do? Well, now the first qubit is, over here, the first qubit is set, right? So that means that the second qubit will get flipped. 1, 0. Okay, so now stare at this for a second. and see if you can convince yourself that this thing is actually not entangled anymore. Okay? Why is it not entangled? Well, remember, not entangled meant you could factor out the states on the qubits, right? And you'll notice here on the first qubit, you have 0 and 1. So that part, you can't really factor that out. But on the second qubit, I have the same term. I have 0 and 0 twice. So I could factor out that 0. And indeed, what this looks like is 1 over root 2, 0 plus 1 over root 2, 1. Okay? Tensor 0 on the second qubit. Okay? So really, it's become plus and 0. So even though I started with an entangled state, the Bell state, right, which is the canonical entangled state, if you will, the maximally entangled state, the control knot has the ability to just totally kill that entanglement. Okay? And of course you can do this, or intuitively you can do this, because unlike the tensor product gates of type 1, we talked about this is a genuine 2-qubit quantum gate. Okay, good. So, page 7, we're almost done for the week. Let us do our first quantum circuit. Okay, or let's say our first slightly non-trivial quantum circuit, which is going to be the circuit that prepares the Bell state phi plus. Okay, actually, I've kind of already given away the answer. Right, because, well, here's your hint. While I kind of read my notes for a second, you can stare at this. And we said that applying the C naught to phi plus, that, takes us to plus 0. So if I start from the state 0, 0, this should sort of give you an idea of how you can then prepare phi plus. Okay, so think about that for a second. Okay, so here's one way we could do it, right? If I have phi plus, okay, first before I do that, quantum mechanics has to be reversible, right? We said all the operators are unitary. So if I can find a way to map my state phi plus onto the state, say, 0, 0, using unitary operators, then I could also invert that entire process and go back from 0, 0 to my phi plus state. And that will give me the preparation circuit, right? So what I need to do is, I already know, from this example, I already know that C naught of 1, 2 of phi plus, right, on 1, 2, this equals to a plus on 1 and a 0, right? So if I next apply, all I have to do to get to state 0, 0, and by the way, whenever we do computations, we typically like our ancilla qubits or all of our work qubits to be initialized to 0, just like you would in classical computation. So I want to get back to 0, 0. If I apply a Hadamard, remember, on this first qubit here, remember that will undo the plus and take it back to the 0 state. And then I'll end up with ket 0 on qubit 1 and ket 0 on qubit 2. And that's ideally what I want, but of course now I want to do this in reverse. So what was the circuit we applied here? The circuit we applied was the following. We said you start with phi plus, right? We applied the C naught, and then we applied Hadamard tensor identity, right? And this took us basically, this took us from the Bell basis, if you will, to the standard basis. And if I want to do the opposite now, I just, invert these operators, right? I mean, these are invertible, so I take the inverse of this first. Remember, I have to do it in order, right? So I take the inverse of this. And so what this means is that the C naught of phi plus is equal to H1 dagger tensor identity 2 dagger 0, 0. And if you stare at these two matrices, they are both symmetric with real entries, so this dagger does absolutely nothing. I can just eliminate the dagger, it'll look identical. Doesn't matter at all. Okay, and then I undo my C naught, right? And so that means I do C naught dagger at H1 tensor identity on 2. Maybe I can write 1, 2 here. And again, the C naught is also symmetric, and it has only real entries, so the dagger really does nothing. Okay, so in this sense, I know now how to start from the 0, 0 state and prepare the Bell state, right? I just do this sequence of gates. That's it, right? So I could work it out backwards. And what does the circuit look like, the diagram? Well, I take 0 and 0 here, right? These are my qubits again. So first qubit is the top, second qubit is the bottom. What I do remember is now, this tells me I have to apply a Hadamard on qubit 1, right? And I want to do an identity on qubit 2, but that's just doing nothing, so I'm just not going to draw anything. And then you need to do the C0 gate. And remember the C0 gate, the target is the second qubit, the control is the first qubit. And that's it. And so the joint state you'll get here will be phi plus. Okay, and we can't write it as a tensor product, so I have to write it this way. Okay, let me very quickly just work that out algebraically, just so you can see how this... Well, actually, do I need to do that? Because it's the backwards of this. Yeah, so maybe I won't do that, because algebraically, you know, if you want to show this works, you just invert, you know, do this computation backwards, right? Okay, so that is all we have for week 2, which are the first 3 postulates of quantum mechanics. Okay. Next week we'll do the third postulate, which is measurement, right? And once we do measurement, then we could talk about things like teleportation, so our first kind of non-trivial task, if you will, using quantum computation or in quantum computation. As usual, if you have any questions in the meantime, do post them to Panda, okay? And assignment 1, remember, is due this Friday, May 1st. The second one will be due next Friday, May 8th. Okay, so until then, have a good week and stay healthy.